Welcome back to the deep dive. If you thought 5G was just about faster downloads on your phone, well, prepare for an architectural X-ray. Today, we're not just defining the pieces, we're revealing the ingenious engineering decisions and subtle interdependencies that power our connected world.
Right.
Think of it as pulling back the curtain on insights often reserved for the pros. And we're doing it with a rather unique lens. Insights gleaned from specialized exam practice questions, like those for the H35-480 certification.
It's a really interesting approach.
Yeah, it's kind of a shortcut, right? A shortcut to being truly well-informed without the textbook slog.
Definitely cuts through the noise.
Our mission today is to give you a deep yet digestible understanding of 5G fundamentals. We'll be navigating everything from the core base station components and how they communicate, to advanced air interface technologies, and even how these networks are put to the test. Get ready for some truly surprising facts and maybe a few aha moments.
Yeah, things that'll reframe how you see our always-on world. And this isn't about rote memorization, Our goal is really to uncover why these technical choices were made.
Why behind it?
Exactly. And what strategic advantage they offer. By understanding these underlying mechanisms, from the precision of beamforming to the agility of network protocols, you'll truly grasp how 5G is poised to transform far more than just your smartphone.
Okay.
It's about building the bedrock of an entirely new era of connectivity.
Okay, let's peel back that first layer then. When we talk about a 5G base station, we refer to it as a GNB. Now, most people know it's where the signals come from.
Sure.
But what's truly distinctive about the GNB compared to, say, its predecessors?
Well, at its core, yes, the GNB, or Next Generation Node B, is the 5G base station, the front line of radio access.
Right.
Its key function is handling that crucial radio interface, transmitting and receiving signals to and from your user devices, your UEs.
Okay.
But what's truly distinctive isn't just a name change from the LTE ENB, it's the radical flexibility in its deployment architecture.
Flexibility. How so?
Well, unlike earlier generations, the 5G GNB is designed to allow disaggregation.
Disaggregation, meaning you can split it up.
Exactly. You can separate its components, even virtualize parts of the baseband unit and move them further into the network or even the cloud.
Okay.
And this architectural shift fundamentally changes how operators scale, upgrade, and optimize their networks. It goes far beyond just handling radio signals.
So it opens up possibilities for what?
Yeah.
Greater efficiency, lower latency?
Both, yeah. It's fascinating, really. A big step up.
That is a crucial distinction. The ability to disaggregate and virtualize, it's not just a hardware upgrade. So if the GNB is the overall base station, where does the real magic happen, in terms of signal processing?
Right.
Is it all happening in one big box, or are there distinct brains responsible for shaping those radio waves?
Great question. So within the GNB, the primary brain you're looking for is the baseband unit, or
BBU.
a BBU. The BBU's main role is to process baseband signals and manage radio access network, or RAN, functions.
So like the computational core.
Exactly. Think of it like that. It's responsible for the intricate work of scheduling when and how devices transmit, encoding your data into radio signals, and dynamically managing radio resources.
Okay, so it's doing the heavy lifting on the signal logic.
It is. But it's important to remember that the BBU doesn't handle the raw power delivery or radio frequency amplification.
Those are separate.
Those are distinct hardware functions, yeah. So if we connect this to the bigger picture, the BBU is essentially dictating how those radio signals are prepared, managed, and optimized before they ever hit the airwaves, making sure you get peak performance.
I can see why you'd call it the brain. But, in this era of cloud-native networks, couldn't that intelligence be moving further into the core? Or even the cloud?
That's a really good point.
What makes keeping this processing at the base station still so critical for 5G, especially given that disaggregation you just mentioned?
Right, and that's where the disaggregation becomes truly clever. Because while some functions can be centralized, absolutely, the really time-critical processing, the stuff that directly impacts user experience, things like very precise scheduling and beamforming decisions, that still needs to happen as close to the antenna as possible.
To minimize latency.
Precisely. We're talking milliseconds, making a huge difference for mission-critical applications.
Right, like remote surgery or autonomous vehicles.
Exactly, those kinds of things. So the BBU's continued role at the base station, even if parts of it are virtualized and distributed, it's really a testament to the laws of physics,
Okay.
and the need for ultra-responsive communication. It's more of a hybrid model, really, balancing centralization with proximity.
That makes perfect sense.
Mm.
Physics always wins, even with virtualization. Okay, so for the network engineers, the folks who have to keep these complex systems running,
Yeah.
knowing exactly what's under the hood, down to the installed hardware in a BBU, that must be absolutely vital for maintenance and upgrades.
Oh, absolutely vital. Couldn't do the job without it.
How do they get that granular visibility? Is there a specific way?
There is. For practical operation and maintenance, technicians rely on specific commands. One of the most common is the LST board command.
LST board. Okay.
Yeah, list board. This command is used to query the hardware configuration of a BBU. It gives them a detailed list of all the installed boards and their status.
Like a system inventory check.
Pretty much. It's fundamental for proper setup verification and, of course, troubleshooting if a component isn't performing as expected.
Right.
It's kind of like checking your car's diagnostic codes, but, for a multi-million-dollar piece of network infrastructure.
A slightly more complex car.
Hmm.
So we've identified the GNB as this versatile base station and the BBU as its intelligent core. Now, the internal conversations within a 5G network, they've become incredibly sophisticated, haven't they?
They really have.
Almost like they've learned entirely new languages compared to older generations. How has this evolution in communication pathways become such a critical differentiator for 5G?
This is where 5G's flexibility truly shines, yeah. And it's a direct response to the need for faster, more agile networks. We essentially have two main communication dialects, you could say, depending on the network setup.
Okay, two dialects.
First, in a 5G standalone, or SA, networking scenario, that's where 5G operates entirely independently of older LTE networks.
The pure 5G.
Right. In that case, the NG interface is used for the control plane communication between the GNB and the access and mobility management function, or AMF.
The AMS, okay.
And this is highly significant because this NG interface replaces the older S1MME interface that was used in LTE.
Ah, so it's a completely new pathway.
It's a clear architectural break, yeah. Signaling a truly independent 5G core designed for next-gen services from the ground up.
Got it. So that's SA mode. What's the other dialect?
Then you have the 5G non-standalone, or NSA, networking configuration.
NSA, right. That's more common right now.
It has been, yeah. It's kind of a pragmatic bridge where 5G often works alongside LTE, leveraging existing infrastructure to get 5G to market faster.
Makes sense.
In NSA mode, the GTPU, that stands for GPRS Tunneling Protocol User Plane,
G2P.
is used for data forwarding between the GNB and the ENB, which is the LTE anchor base station.
So it tunnels data between the 5G and LTE parts.
Exactly. This protocol is absolutely vital because it ensures seamless user data delivery as your device moves or communicates across both LTE and 5G cells.
So you don't drop your connection.
Precisely. It provides a smooth transition while the pure SA networks are still being built out. It's a clever way to get the best of both worlds, at least temporarily.
So it's not just about what the components are, but how flawlessly they can speak these different languages and coordinate. That's key for a seamless experience for us.
Absolutely.
But beyond just these evolving communication pathways, what's ensuring all these critical messages, the control signals and data packets, actually get where they need to go reliably?
Reliability. Crucial point. That's where a protocol called SCTP comes into play. Stream Control Transmission Protocol.
A CTP.
It's the primary protocol for ensuring reliable and ordered data transfer between network nodes for control signaling, especially in critical 5G interfaces like NG and XN.
So it guarantees delivery.
It does, and in the right order. But what's genuinely insightful about SCTP isn't just its reliability, it's its ability to manage multiple independent data streams within a single connection.
Multiple streams. How does that help?
Okay, imagine trying to deliver critical medical commands to a remote robotic surgeon. If one instruction, say a minor status update, gets delayed for some reason, other vital commands, like stop cutting, can still get through on a separate stream without waiting. It prevents a single delay from causing a system-wide bottleneck.
Wow. Okay, so it avoids head-of-line blocking within the connection itself.
Right, exactly. That multi-streaming capability is fundamental to the ultra-low latency and hyper-reliability needed for mission-critical applications, where every millisecond, every instruction truly matters.
That's incredible.
It's almost like the Postal Service, but with the guarantee that every letter arrives in order. And if one street is blocked, it finds another way, something early internet protocols just couldn't reliably do for critical data.
That multi-streaming for mission-critical uses,
Yeah.
that's a profound insight. It really highlights it's not just about speed, but resilience and intelligent traffic management.
Absolutely.
So moving beyond these foundational communication layers, what about the air interface itself? What are the cutting-edge technologies that make 5G so uniquely powerful and efficient in how it actually sends signals through the air?
Right. This is where 5G truly innovates, transforming how radio waves are used. One of the most talked about advancements is the combination of massive MIMO and beamforming.
Massive MIMO and beamforming. We hear those terms a lot.
We do. And to truly appreciate beamforming, think about how radio used to work, like shouting into a crowded room, hoping someone hears you.
Okay, broadcasting wide.
Exactly. Now, with beamforming, it's like having a precisely aimed laser pointer. The primary purpose of beamforming when using massive MIMO technology is to reduce interference by directing the signal toward the intended user.
So focusing the energy.
Precisely. Instead of just blasting a signal in all directions, beamforming shapes the radio waves into narrow, focused beams, sending that energy directly where it needs to go.
And that's not about just cranking up the power.
No, not at all. It's about surgical precision. And that precision significantly improves signal quality, reduces interference for other users, and is absolutely crucial for dense 5G deployments, where many devices are packed into a small area.
Ah, okay. That's the aha moment right there.
Yeah.
It's accuracy and efficiency, not just brute force power.
You got it.
Interesting. What else is new in the air interface?
Another core innovation is in the very nature of the radio waves themselves, the 5G new radio, or NR, air interface.
5G NR.
Yeah. A key characteristic is its use of orthogonal frequency division multiple access, OFDMA, for both uplink and downlink.
OFDMA, like in advanced Wi-Fi.
Similar concept, yes. It means data is split into many smaller subcarriers transmitted in parallel, allows for highly efficient use of spectrum and better handling of multiple users simultaneously.
Oh.
But what's truly ingenious here is that NR also supports scalable subcarrier spacing, unlike LTE, which had a fixed 15 kilohertz spacing.
Scalable spacing, what does that allow?
Well, this isn't just a technical feature, it's a fundamental design choice that makes 5G incredibly versatile, a real chameleon.
A chameleon, how so?
For a self-driving car needing instantaneous data, it might use wider, faster subcarriers, more bandwidth per chunk.
Okay.
But for a tiny agricultural sensor reporting soil moisture once a day, it can switch to ultra-narrow, highly robust subcarriers that travel further and consume minimal power.
Ah, so it adapts the radio waves to the specific need.
Exactly. It allows 5G to dynamically reconfigure its airwaves, perfectly suiting vastly different applications simultaneously within the same network. That flexibility is key.
That chameleon analogy really paints a picture. Precision, flexibility, efficiency, clearly built into every layer. But okay, before you can even use these advanced features, your phone has to find that network, right?
Absolutely. The very first step.
What's that critical handshake? How does your device make that initial connection?
This is literally the foundational step your device takes. When your phone tries to connect to a 5G cell, it looks for very specific signals. Beacons, essentially.
Beacon.
One of the most important is the PSS, the primary synchronization signal.
A BSS, okay.
Its purpose is to allow the user equipment, your UE, to acquire time and frequency synchronization with a cell.
So this is like the network's heartbeat.
Kind of, yeah. Think of it as the network broadcasting a very specific, recognizable pulse. Your phone absolutely needs to detect this pulse and align its internal clock and frequency with the network's.
Before it can do anything else.
Exactly. Before it can even begin to read other crucial system information like network IDs or available services, it's the silent, invisible handshake that kicks off every single 5G connection. Without it, your device wouldn't know when to listen or where to find further instructions. It would be completely deaf to the network.
It's incredible how many layers of sophisticated tech down to that initial pulse are involved just to get connected.
Yeah.
Okay, finally, with all this incredible engineering, all this intelligence, how do operators know if a 5G cell is actually delivering on its promises? How is performance measured in the real world, beyond just theoretical specs on a data sheet?
Yeah, real-world performance. That measurement is absolutely vital for maintaining a high-quality network, for ensuring customer satisfaction.
Sure.
when assessing the coverage and capacity of a 5G cell during single-site verification, which is a crucial test after a new cell is deployed or upgraded.
Right, checking the installation work.
Exactly. The primary key performance indicator, or KPI, is IP throughput.
IP throughput, so data speed, basically.
Essentially, yes. This metric directly reflects how much data a 5G cell can deliver under test conditions. It tells us two very important things. First, it indicates the signal strength and reach.
That's the coverage part.
Right. And second, it shows how efficiently the network resources are being utilized to deliver that data, which speaks to capacity.
IP throughput is crucial, yes. But what's often overlooked, I think, is how challenging it must be to optimize this KPI in a real-world dynamic environment.
Oh, absolutely.
It's not just about raw speed in a perfect lab test. It's about consistent speed under varying load, interference, people moving around.
You've hit the nail on the head.
So what's the true insight here for maintaining that consistent high-speed experience we all expect?
That's a critical distinction. The true insight here is how sophisticated network analytics have to be now. We're moving beyond simple measurement to predictive optimization.
Predictive optimization.
Yeah. Operators are constantly analyzing traffic patterns, interference levels, device behavior, trying to anticipate congestion and dynamically adjust network parameters on the fly.
So it's proactive, not just reactive.
Exactly. This ensures that the promised throughput holds true for millions of users, not just in static test scenarios, but in the chaos of real-world usage. It's a continuous, intelligent balancing act to keep those high speeds consistent.
So here's a final thought for you, our listener. Given 5G's fundamental design for precision, reliability, and scalable capacity, how might your understanding of these specific technical details change the way you perceive the future potential of connectivity? Beyond just smartphones, think about self-driving cars, smart cities, critical infrastructure. How do these technical nuggets, the beamforming, the multi-streaming SCTP, the scalable NR, how do they show you the true bedrock of that connected future? And perhaps, what are the unexpected challenges that might come with managing such sophistication?
Lots to think about there.
Definitely something to mull over until our next deep dive.